Mondays are terrible. All right, so let's take a look at this. Remember that our pattern triangle here, our pattern triangle is the legs are the same, and the hypotenuse is the leg times the square root of 2. Okay? That's the idea. Now, instead of writing leg root 2, we just put a variable there instead of writing out the whole word leg, because the legs of the right triangle, we just said n instead of leg. But it's the same idea. And the goal here is always find the value of n, because if you find the value of n, you know the lengths of both the legs, and you just take whatever that value is and multiply it by the square root of 2, and that's the hypotenuse. That's what we're doing, finding the length of that leg. So whatever triangle we have and however it's set up, for example, if we look at, say, number 20, where we have root 5 over 5, okay, well, I know leg times the square root of 2 has to equal root 5 over 5, or n times the square root of 2 has to equal root 5 over 5. Now, once I have that set up, now all we have to do is the arithmetic to solve it, or the algebra to solve it. And one of the tricks we have, in order to undo multiplication by the square root of 2, I have to divide by the square root of 2. Now, for a lot of people, that creates a little bit of algebra headache. How do I divide root 5 over 5 by the square root of 2? That's like multiplying a root 2 into the denominator. It's multiplying by 1 over root 2. It's the same as dividing by 2. Root 2, excuse me. So now I've got 5 over 5 root 2. Root 5 over 5 root 2. I have to rationalize that. Root 5 times root 2 is root 10. Root 2 times root 2 is 2, and 5 times 2 is 10. And I have that my side is root 10 over 10. And that's how we solve that. It does take some comfort working with radicals to do that. That's definitely one of the hardest problems we had yesterday, or Friday. But a lot of the problems were a lot more basic. Plenty of the problems were more like 15. 15, again, we knew it was isosceles, and this side is the square root of 6. My pattern triangle, again, leg times the square root of 2. So leg times the square root of 2 is root 6. Again, we solve by dividing by the square root of 2. Now, remember, our pattern, whenever I get a square root in the denominator, we do 3 steps. I reduce, I rationalize, and then I reduce again. But if at any point I'm done with having a square root in the denominator, I can quit. Basically. So, root 6 over root 2, can I reduce that? Yeah, they're both under a radical, so the 6 over 2 becomes a 3 over 1. Well, root 3 is just root 3, root 1 is just 1. Aha, n is root 3 over 1, or just root 3. That's it. That's how we solve that. By using the pattern triangle. You have to know your pattern triangle. And the best way to do this is just draw the pattern triangle right next to the regular triangle so there's no confusion about what's what. Especially in this new section. Because right now I only have the legs, which are congruent because it's an isosceles right triangle, and the hypotenuse. I only have basically 2 different lengths. The one today is going to have 3 different lengths. So again, it's very important that we get this drawn with the correct triangle there. Okay? Are there any others from the homework that you'd like me to go over? Just a quick reminder, tomorrow is tonight and Wednesday night are registration. Some of you have appointments tonight, some of them on Wednesday night. If you're going to sign up for math again next year, if you're a sophomore right now, basically it's optional. You got your 2 credits. You don't have to take math next year. About 85% of Milton students do take a third year of math, and your third year is Algebra 2. Everybody signs up for Algebra 2. You don't sign up for honors or intermediate, you just sign up for Algebra 2, and then the test scores that we take later in the year help determine who goes into honors, who goes into intermediate. And if you don't like where you're placed after the test scores, if you don't like which one you get put into, you can always appeal that decision. But for now, everyone just signs up for regular Algebra 2 if you're planning on taking a class next year.
Let's say you somehow, hypothetically, get put into honors.
Yes.
Can you say, no, I don't want to do honors?
Yes.
Okay.
You can appeal whatever placement you had. And you can always drop it down if you need to. That's not a problem. So if you test into honors and you say, I'd rather just do regular Algebra 2, yeah, you can make that switch. That's not a problem.
Okay, so what if you're like at the very top of
regular?
Yeah, and you want to do a high.
You could, again, we have an appeal process. The placement is not final. You may go into guidance and go through there's a little appeal process you go through, and they kind of talk to your math teacher and see. That's where we don't want just the number to make the determination. And for people who are borderline like that, if you want to be in the higher class, that's where working with your math teacher and whoever else, then we can say, yeah, no, they can handle honors, that'd be fine. Or maybe you might want to think twice about that sort of thing. You know, that's where the individual decision making and the human factor comes in rather than just numbers. So, still a people business. You know, that's the way it works. So, but anyway, just remember, like I said, about 80 to 85% of Milton students take a third year of math. If you actually are a freshman right now, I believe you are going to be required to have 3 years of math. So, and either pre-calc or algebra 3 and problem stats or something like that. So, all right, and that's a new state law. So that's not something the Milton High School decided. That's a state law that got passed this last fall. So, all right, let's do 30, 60, 90s. Our other special case is the 30, 60, 90 triangle. Now, this comes from the equilateral triangle, because sometimes people go, well, why is that so special? Other than, 30, 60, 90, it's a nice, gosh, 30 times 2 is 60, 30 times 3 is 90. That's kind of nice. But where does it come from?
Kind of like 1, 2, 3.
Yeah. It comes from the equilateral triangle. Now, in an equilateral triangle, we know all the sides are the same. What are each of the angles? Okay, what measure are each of the angles? No. There are no right angles.
Wait, I'm confused.
What in this, we know these 3 angles are all congruent. What's their measure?
60.
60 degrees, yes. Okay? So what we're going to do is we're going to call each side length, then I'm going to give each side a measurement. I'm going to call it 2y. All right? I'm going to call each side 2y. Now, you'll understand why here in just a second, so we don't wind up with fractions. I don't want to wind up with a fraction. So that's why I call each side length 2y. Now, if I put this altitude in, the altitude, you recall, goes from the vertex and is perpendicular to the opposite side, so I'm making this a right angle.
So we're not doing fractions.
So now, this is 90, this is 60, means this angle up here is, these 2 angles are each 30, aren't they?
30, 60, 90.
And we now have our 30, 60, 90 triangle. It's half of an equilateral triangle, isn't it? Okay? Now, if it's half, that means that this side right here, which is 2y, if I just want to take half of that, what's that going to be? Y. See, if I made this just y, then this would have to be 1/2 y. We'd have a fraction. And again, we don't want to have to deal with a fraction if we don't have to. So we get that simplified. So here we go. There's our special triangle. Our 30, 60, 90 triangle has a short leg of y, a hypotenuse that is twice as long as a short leg. Or a short leg which is half as long as a hypotenuse, however you want to look at it. But the short leg and hypotenuse have a very easy relationship. One is twice as much as the other. What's tricky is the long leg. The long leg requires a little bit of work, so let's try to figure that out. By Pythagorean theorem, it's short leg squared plus long leg squared equals hypotenuse squared. Right? That's Pythagorean theorem. Yes, because otherwise the squared would only be on the y. When I take this off the y, that becomes 4y squared. I take the parentheses away. Okay? So y squared plus n squared is 4y squared. We can subtract a y squared from each side. So I get n squared equals 3y squared.
Oh, okay. I figured it was going to be 4, but then... So you
No, just it's like 1y squared, right?
Okay, I get it now.
Okay? So, we take the square root of both sides. Square root of n squared is just n. Square root of y squared is y, but the square root of 3 does not simplify. So this long leg is the short leg times the square root of 3. And what makes this kind of confusing for a lot of people is people go, oh, it's like 1, 2, 3. Like your 30, 60, 90 is like 1, 2, 3, right? That's what you said. It is like 1, 2, 3, except here it's not actually 3, it's the square root of 3, which is less than 2. Square root of 3 is about 1.7. So the 3 is actually the long leg, the square root, because it's square root of 3. 2y is the hypotenuse. But that is our triangle. Now, some people want to think of it, it's easy for, instead of variables, to think in terms of short leg, okay, this is 2 times the short leg for the hypotenuse, and this is short leg times the square root of 3. That's the pattern. Now, I didn't write out the term short leg, I just put y down, because it's a lot quicker to write y than short leg, right? But it doesn't matter. It's the same basic idea. The trick, obviously, is if I know the length of the short leg, the other two are really easy to find, aren't they? So I always want to try to find the length of the short leg if I'm not given that. If I'm given the length of the short leg, it's really quite simple. For example, if I'm given that the length of the short leg here, if I'm given that the length of the short leg is 7, then the hypotenuse has to be how long? Twice as much as the short leg, which would be 14. And the long leg is the short leg times the square root of 3, which would be 7 times the square root of 3. So the key is finding the length of that short leg. Here are some examples with the 30, 60, 90. Now, again, this is one of those times where it really can pay off to draw your reference triangle next to it. Okay? Short leg, long leg, short leg times the square root of 3. These are 30, 60, 90 triangles, so we'll just go ahead and work on that assumption for now. Hold on. Here, we'll mark it in, actually. Okay? Here I'm given the hypotenuse is 10. So how long is the short leg going to have to be? 5. And the long leg? Short leg times the square root of 3. All right. This one I'm giving the hypotenuse is 9. And again, it's short leg, long leg, short leg times the square root of 3. If the hypotenuse is 9, how long is the short leg? 4.5 or 9 halves. And how long is the long leg? 9 halves times the square root of 3. Yeah. This is a little more complicated. Here I'm giving you the long leg. Again, we can draw our reference triangle in. I have short leg, hypotenuse, long leg. 8 is the short leg times the square root of 3, isn't it? Now I have a little bit of algebra to do. Divide both sides by the square root of 3. So the short leg is 8 divided by the square root of 3, which I have to rationalize. Root 3 over root 3 is 8 root 3 over 3. Aha! It doesn't reduce any further, so that's my short leg. How long is the hypotenuse going to be? Well, it's the short leg times 2. 2 times 8 is 16 root 3 over 3. Yes?
So is it always going to be root 3?
For a 30, 60, 90, yes. Now, actually, I mean, it could be, here it's not root 3, it's just 8. I mean, I could say that side is root 6, but the pattern is always root 3. The pattern is always root 3. Notice what I've done here. I've set up 3 30, 60, 90 triangles, all kind of oriented the same way. Each of them has one side that's 2 root 6, but in each of them it's a different side. But it doesn't matter because my pattern is still the same. Okay, short leg times the square root of 3, 2 times the short leg. Here I know the short leg. So 2 times the short leg would be, what would that be? 4 root 6. And the long leg would be the short leg times the square root of 3. Now I got a little work to do. Root 6 times root 3 is root 18. And can I simplify that?
9.
Yeah. So in fully simplified form, that would be 6 root 2. Okay? This time, I give the hypotenuse. The 2 root 6 is the hypotenuse. What's the relationship between the hypotenuse and the short leg? Hypotenuse is? Double. 2 times the short leg. So half of 2 root 6 would just be root 6. So this side would be root 6 times root 3. Or root 18, which you already have established is 3 root 2. This time the 2 root 6 is on the long leg. So again, we compare. The long leg is the short leg times the square root of 3. Leg times the square root of 3 equals 2 root 6. I have a little bit of algebra to do. What am I going to do to both sides? I'm going to solve that for L. Divide by root 3. Cancels out here. Does that reduce? Yeah. What's that going to be? 2 root 2, because the 3 and the 6 reduce to a 2 and a 1. And root 1 is just 1. And so what's this hypotenuse going to be? 4 root 2. Short leg times 2. That's the way these things work. But again, you have to have your triangles memorized. We have our two basic triangle patterns. The one from Friday, which is leg times the square root of 2. And we have the one from today, the 30, 60, 90, which says short leg times the square root of 3, and 2 times the short leg.